star formation is fairly common when we look out in the galaxy or other galaxies even, but on average, one new star turns on in the Milky Way galaxy per year. On human timescales, that's really slow, but on astronomical timescales, that's pretty good. When you form stars in a cluster, you're going to tend to form mostly low-mass stars. Okay? So mostly low-mass stars will form some intermediate mass stars. And the high-mass stars that don't live very long and they go supernova when they die, they're quite rare, actually. So let's look at the two extreme masses. You can't have a star with a mass that's less than 8% the mass of our sun. Right? 8% the mass of our sun. Because then the core pressure and the core temperature never gets extreme enough for hydrogen fusion to start and become stable. So if you form something that's less than that mass, we're going to call it a brown dwarf. You can call it a failed star. And because low mass stars are the most common that form, we think that brown dwarfs actually are even more common, just continuing the trend. And they're hard to find because they're not very bright. They don't have fusion. But if you look in an open cluster and you switch to infrared and you try to find as many of these things as you can, right, each one of these little circles indicates a brown dwarf. They're really, really common. So we think that brown dwarfs probably outnumber stars. So typically, gravity would squeeze your star denser and denser and denser until the pressures and temperatures got extreme enough for fusion to start. But when you're in this special case, about 8% the mass of the sun, it can never actually get itself dense enough in the core to start fusion. It's because another type of pressure takes over. And this one is going to be called electron degeneracy pressure. So usually when you have energy levels, the electrons are not occupying every single possible state. But as you squeeze down this brown dwarf and the matter gets denser and denser and denser, the electrons get packed into every single energy state. And so there's nowhere else for them to go. So electron degeneracy pressure supports a brown dwarf and prevents any further collapse, which would have started fusion. So we talked about the smallest masses of stars, but what about the largest masses of stars? So the more massive a star is, the more powerful it becomes. And if it gets too powerful, it'll actually start to blow away its own mass out into space. And so you reach this boundary where stars don't seem stable anymore. That boundary seems to be about 150 solar masses. Despite that, we do see stars that are more massive. The most massive star we've discovered is R136A1. Here is its approximate radius compared to the Sun. And its mass is about 265 times the mass of our Sun. So that's definitely bigger than what a typical main sequence star could be. So this star, we'll call it a hypergiant. And hypergiants will continue to lose mass, and as they do, they'll be able to live a little bit longer. But some of them go supernova before ever reaching that stable limit.